Right, great. Hello, everybody. I think we'll get started now. So, welcome to my talk. Hopefully, this is going to be just kind of a couple of stories about who I am, what I do, what we do, and how we use kind of open tools and open data to kind of make science better in general, right? So, my name is Jacob Tomlinson. I'm the lead engineer for the Met Office Informatics lab. I like stuff like this. So, to kind of preface my whole talk, I'm not a scientist, I'm an engineer in a team of scientists, okay? So I'm hoping to get the science right, but this is more of a technical talk. So for those of you who may not know what the Met Office is, the Met Office is a UK government department. We do weather forecasting and climate research for the whole globe and the UK. It's a very old organization. It's been around since the 1800s. We used to be a military organization. It kind of came out of the Navy. It's now a kind of separate trading fund under UK government. And we're based down in the southwest, down in Exeter. So a lot of people know us for stuff like this, right? You see the weather on the TV, and on the internet, and on the apps, and all those different things. But we also, that's just kind of like the very surface of what we do. We do all sorts of other things in all sorts of different industries, from everything from kind of telling wind farms which direction to point their windmills, to telling airports how much de-icer to spray on an aeroplane so that they completely de-ice the plane but use as little de-icer as possible, because aviation de-icer is very expensive. So we've got loads and loads of products that kind of, it's a huge range of stuff, but it's all built off a very large data set that we generate ourselves using a physical weather model. I specifically work in a team called the Informatics lab. So we're kind of like the R&D team, like the innovation area. We're a small mixed discipline team. Within this organization of 2,000 people, there's 10 of us that sit in a room. We're a mix of scientists, engineers, designers, and we're looking at how we can progress the organization, how we can use different technologies, different techniques, change our processes to make us better going forward, and to help us kind of hit our mission a bit better. So we have a very large IT infrastructure within the organization, as you can imagine. We stay away from that completely. We act as an external body almost. So everything we deploy within our team, we put on AWS or Azure or in the cloud somewhere. We then access our data through the kind of standard data APIs that we make available to everybody else. We try and dog food our own systems as much as we can. And any time that we can't access something that we need, then we try and go back internally and make it available so we can then consume it from the outside. And it makes it more accessible to everybody else. We also, because we are part of the government, we're publicly funded, we just make everything open. We try and be as open as we can. There is like a whole commercial side of the business, and their goal is to make money from selling these products to customers, but those are products that are derived from the data that comes out of the core business. So we in the lab are very open. We code in the open. Everything we do just gets dumped onto GitHub. There's I think we have like 3 private repositories, and that's just because we accidentally put some API keys in them, and so we probably need to do a big squash at some point and get those keys out and then make them open. We're kind of, following on from the last talk, if you saw that one, we are a bit naughty in the fact that we do just dump lots of stuff onto GitHub, and there's the bulk of what we put out there is not necessarily useful, and so we're putting a lot of effort into trying to find what people find interesting and what we can take from that and build a community around. I'll talk a bit more about other stuff that we do that's a bit more actually open source rather than just coding in the open in a minute. So I was just going to spend a bit of time telling you about what kind of data we have and how we generate it and what we're trying to do with it. So the kind of thing that we do is we run physical weather simulations on some supercomputers that we have in our basement, right? We've just spent a decent chunk of money on a next-generation supercomputer. We've built another building and installed this one, and it's a really powerful machine. And we use this in a process for predicting the future, right? It's quite there's not many businesses that can say that their whole business model is based around predicting the future, so it's quite an interesting space for us to be in. But we do this scientifically, right? So the first thing we have to do, in order to predict the future of the atmosphere, we have to know exactly what the atmosphere looks like right now. So we have weather stations all over the country, we have thermometers and radars and all that kind of stuff. And we collect everything for the UK. We've got partner organizations all around the world. Every country has some kind of Met Office that does weather forecasting, and they collect all their measurements. And then we all share. There's a really nice collaboration. There's a global thing where everybody shares their information. And one of the reasons that we have to do that is because you can't actually run a physical weather simulation without entire global coverage, because you have to know, if you want to run a local weather simulation, you have to know what the edges look like in order to see if there's any weather systems coming in from the outside. So if you want to start from scratch, you have to have continuous circuit. You can't have any edges. So you have to do a global forecast. It's a sphere, so there are no edges. That's great. But in order to be able to do that global forecast, we have to share that information with everybody else. So we're ingesting millions of measurements, per day into a big data store. And these are all point measurements. These are all little bits of data, temperatures and wind speeds and all kinds of stuff that's come from our equipment and our partners' equipment. And that all gets loaded in. But as you can imagine, they are not evenly spaced. There's often more weather stations in highly populated areas. You can imagine this is, we're currently on an island, so there's less coverage over the ocean areas. We get loads of measurements off airplanes as they're moving along and boats and all that kind of stuff. But we have to run this on a supercomputer, right? We have to run a physical weather model that requires a grid. So we have to do a big first step where we take all of those point observations, we interpolate between them, we do a load of smoothing, and we convert that into a gridded data set that explains what the atmosphere looks like right now. Once we've got that model, once we've got those initial conditions for the model, we then run something that we look after in-house called the unified model. It's a physical weather model that predicts how that environmental system is going to change going into the future. I'll explain a little bit more about kind of how it does that in a minute. But once we've run the model, we get lots of data coming out, vastly more data coming out the other end. And then we do lots of post-processing. We have lots of downstream systems that pull the data out of the stream as it's coming out of the machine and generating all the downstream products. So like the weather map I showed you before, that's one of the products. Kind of web interfaces and apps and things that we provide to our customers, those are the products. Those are kind of more, smaller data sets that are being derived from this larger data set. And we end up doing a lot of kind of web development, app development, that kind of thing to visualize the data and try and communicate it to people. Because, we don't want to just dump loads of raw data at you. We want to, if you're a business and you're trying to do a thing, we want to tell you how to do your thing. If you're a supermarket and you're trying to figure out what to order, but, the weather is a big factor in what supermarkets need to order. If it's going to be hot, then they're probably going to need to order barbecue stuff, especially if it's on a weekend, That's their business need. They don't actually care about the weather. They care about what their stock change is going to look like. So we try and build products that really help them to do that. The actual machine itself, it's a nice machine. Technically, we have 3 machines. Sometimes we group them together because it makes the stats look better, right? But we have 3 discrete machines within our data centers, which, according to the notes on my slide, I can't remember how accurate they are, but they are the 11th, 38th, and 39th fastest machines in the world, as of whenever those numbers are from. I think that's from around January. So we'd probably be lower down that list right now. Everybody's building new supercomputers all the time. The actual machine weighs 140 tons. It can calculate at 23 petaflops, and it uses 13 megawatts of electricity, right? That's a vast amount of electricity. So the data that comes out of that is big, right? We have lots and lots of data coming out of it, and it's hard for us to move that data around. Once it comes out of the machine, we put it into archive, and that's where it sits. As it's coming out of the machine into the archive, we're deriving all of our downstream products, but then we've got this big archive full of stuff. And because we are part of the government, because we have this kind of archiving responsibility and this historical responsibility, we try and keep as much as we can. We keep a ridiculous amount of data. So I was going to do a quick hands-up thing. Who here is worrying about dealing with data in your organization? Who here has kind of data issues? Okay, I see a few hands. Who here is dealing with kind of more than about a terabyte of data within your data set? Okay, see a few hands. Anybody dealing with more than a petabyte of data? Yeah, another hand. Cool, excellent. So hopefully you understand that in the realms of working with these amounts of data, we have these big issues. You've got all these massive organizations like Google and Facebook that are at the kind of exabyte scale. They're dealing with ridiculous, vast amounts of things. But we're dealing at a petabyte scale situation. Ooh, that's exciting. Can I have my slides back, please? Wow. I'll keep going for a minute until they reappear. But we have currently in our archive, as of January, we have some figures from January, we've got about 40 petabytes of data just sitting in our archive at the moment. That, because of the rate that we run the machines, that's increasing at around 200 terabytes per day. So we expect by 2020 we'll be close to 300 petabytes of data. I can see myself. Oh, there we go. Yeah, cool. So we will have around 300 petabytes of data in 2020. We're generating all these products for people as we're building all of this data, but there's so much more value in there that I'm sure we can be deriving. But we also have a responsibility to make this data open, right? We're publicly funded. This machine is the property of the taxpayer. We have a responsibility to make as much of our data open as physically possible. But I mean, does anybody here want to just download the archive, right? Have you got anywhere to put it? We can try and give it to you, but the actual bandwidth cost for us is going to be enormous. The storage cost for you is going to be enormous. So it's kind of like we're in a weird situation where we want to give you the data if you want it, but there's just so much of it. So we are part of the Open Data Government Plan. We have loads of data sets that we make available. Some of them are REST APIs where you can consume bits and pieces. It's generally small amounts of information. It's usually some of the downstream products that we've derived. So one of our more popular data sets is the 5 to 7 day weather forecast, the same kind of thing that you would see in the app or whatever. So you can put in a location and it gives you back temperatures every hour going forward into the future, that kind of data set. We've also got a load of kind of static data sets to do with climate and to do with kind of historical weather. We've got a nice data set which will give you information going back 30 years, but it's very, very small. It's been compressed massively, it's been reduced massively. I think that data set's kind of in the tens of gigabytes. So we've had to take all of this data and pull out what we think will be useful to people, but it's not always easy for us to figure out what that is. So it's quite easy for us to think that makes us weird, right? We do some weird things. We generate our data with a supercomputer, right? I think it's quite an unusual business model. A lot of organizations are collecting vast amounts of data. If you think about Facebook or something, they're collecting data from all of their users, whereas we're taking in a relatively small amount of data, blasting out loads and loads of compute time to generate massive amounts of data, and then we're trying to consume that back down into a product again. So we've got this big kind of expansion phase. So that does make us a bit unusual in that sense. One of the things about that data that makes us unusual is what that data looks like, right? We are trying to deal with all sorts of big data processing technologies. Big data is one of those funky buzzwords at the moment where it's a bit too hand-wavy, but we do need to deal with things on a large scale. But a lot of data sets that people seem to be dealing with are tables, right? Your data will fit into a table somehow. You can, whether there's some joins in there and you've got a few kind of tables linked together, you've still got that, that kind of standard model that you can expand. But for us, if you think about a weather model, there's a vast number of dimensions in there, a really, really unusually large number of dimensions that we've got to deal with, and that makes it quite hard to put it into a table because the data is really, really, really nested. So I'll just show you a few dimensions here, right? If you just imagine the UK or Europe or something, you've got latitude and longitude, right? We've broken it up into a grid, so you can see this latitude and longitude. But the weather model that we run is three-dimensional, so you've got altitude as well. So you've got these three kind of dimensions. You could probably store that in some kind of relational database. But then we're going forward in time. So as we run the model, we'll start at now, and we're going to go an hour into the future, and an hour into the future, and an hour into the future. So we've got these kind of cubes of weather for each hour going into the future for that time. Now, within that cube, there's lots of different variables. There's all the things you care about: wind speed, humidity, pressure, probability of rain, all those different bits and pieces. So that's a whole other dimension added to that. Then we do this thing called ensemble forecasting. So we know that within what we do, there are margins of error within the physical calculations that we know, right? Our model literally runs physics equations. They're physics equations that you could kind of test out on in a bench at school kind of physics equations. But when you couple them all together, you start getting complex weather systems coming out of it. But they're such complex systems that they kind of follow the laws of chaos theory. So within chaos theory, if you tweak something very small, you can get a wildly different output within that system. And we know that our margins of errors are big enough that if we move slightly within our margin of error, we'll get a completely different forecast or a slightly different forecast to what's going on now. So what we do is when we initialize our model, we give a little bit of flutter within those margins of error that we're comfortable with, and then we get this spread of uncertainty into the future. And then we can see whether there's any clusters, whether there's lots of them agreeing with each other, then we can give strong confidence that something is going to happen, and we can give much better probabilities. But it means that for every single one of these forecasts, we're then running it 30 times. So we've got all of these different, you've got each hour future going out, but then we've got 30 versions of that hour as well. So you've got this vast spread. And then you imagine we update this data set every hour, right? We run this model every hour. For some of our models, some of them we run every 6 hours because they're just massive and we can't run them any more frequently than that. But it means that our data's got all these funky dimensions. And there's different ways of storing that and different ways of handling that. But one of the things that we struggle with is because of the fact that we run the model every hour, most of our customers, most of the people that are consuming our data, they only want the most up-to-date forecast. If you're looking at something that's going to happen in 3 or 4 days' time, you want the very latest run. You don't want the run that we did yesterday. You want the run that we did the last hour. So that data goes stale really quickly. It expires, and we have to, we keep this stuff, right? But for most customers, we've basically thrown it away. We basically don't need it anymore. So, that stopped, and that's still going. OK, so as an organization, we've spent a long time thinking about how to store this data. And this is just one of the things that we take into account when we store the data is ways of storing two-dimensional, three-dimensional data. And this pattern is called a Z-order curve, but it's something that you might be familiar with Google Maps, right? So everything is broken up into little tiles, and as you zoom further, each tile is broken into 4, and you can see those, and it reloads those at a higher resolution, and then you zoom into one of those tiles, and it breaks that into 4, and as you're going down, you're getting more granular. So that's called a quad tree. And for 3 dimensions, you can get arc trees as well. But there is storing your data like this makes it easier to access that, especially when you're kind of seeking on disk, you're going left and right. Because of the Zs within the data, if you want to find data that's close to it, it's stored close to it on the disk as well. If you almost imagine those lines as like bits on a disk being stored, right? So as we're moving around the data, we're not getting too far away, and we can traverse quickly. But it means that we've got to have some like bespoke data sets. Where am I? Ooh, slides. That's better. OK. So it does sound like we're unusual. We store things in an unusual way. We process things in an unusual way. But we found increasingly that we're not unusual. Lots of people look at our data and think, well, you're weird. I speak to a lot of people at conferences, and I start telling them about our problem, and they're like, oh, that sounds really interesting, but I have no idea how I can help. But we found lots and lots of people that are working on similar things. Not necessarily to do with weather forecasting or environmental science or meteorology or anything like that, but people that are dealing with these large multi-dimensional data sets, people that are generating data with supercomputers. Quite a lot of product design these days is done with a supercomputer. If you're designing like a detergent bottle or something, you might put the shape into a physical simulation and drop it from a height within this physical simulation, see how the bottle splits at different heights, and see if you can tweak your design so that it doesn't split, and you can drop it from higher and higher, and the bottle is more robust. And one of the ways that you can test that out, instead of like making loads of prototypes and dropping them off things, you can do physical simulations on the supercomputer. Medical imaging is also a really interesting area for us because the developers in that sphere of technology are thinking a lot about visualizing three-dimensional data, how they can visualize different data sets. And so one of the things one of the guys in our team did recently was to, oh no, that's not gone. There we go. Oh, yeah. So one of the guys in our team took a medical scanning open source project that was for looking at brain scans and put a hurricane into it. So we just spent a little bit of time hacking around, getting our data into a format that their system would like, and then managed to draw up some quite nice, this was just a screenshot of a web browser, I took the web browser out, right? But this was a browser, you could manipulate the hurricane, you could drop down through the different levels and things. And that's great, that's a way that we can build on top of other projects that are looking at similar things. And that wouldn't have been possible if those people hadn't made that library open source. So we are generating all of this data. We're trying to collaborate with people on how we can work on this data. But as I said at the beginning, we're deriving lots of things as it's coming out of the machine, right? We're deriving all these products, and we know that we're looking for these products. We've kind of spent a lot of time thinking about what a customer's going to want, and we work out what data we need to get that thing. And so as the feed is coming out of the supercomputer, we can pull out the bits of data that we need and generate the product. But that research, that insight into what the customers need has come out of kind of people thinking about a problem and working through it, and then doing some exploratory research to figure out whether they can get that out of the data. But doing that kind of thing is a bit like creating a train, right? you know where you're going to start, you know where you're going to finish, you want to do it reliably, you want to do it every hour, so you spend a lot of time making something that's very robust, very resilient, but extremely inflexible. You can't just say, oh, I want to go over here now, right? A train goes from one place to another place, and you can't change that. And for exploring these new products, for exploring these new things and these new advances to science within our data, we need something a bit more like an all-terrain vehicle, something where we can go off-road, something that we can still go 100 miles an hour if we've got an open straight in front of us, but something that we can slow right down and then go over all the rocky ground. I appreciate that's a bit of a tortured analogy, so apologies for that. But the only way that we can do that is by collaborating with other people and figuring out what other tools we can use. So this is just a range of stuff that we use for analyzing large data sets. You know, as I said, we've got petabytes of stuff. At the moment, a lot of our downstream products are using gigabytes of that to generate things, and we want to be able to scale that up. We want to be able to analyze terabytes of data really quickly so that we can find insight. So a common workflow for our staff is to get some data out of our archive, put it onto some kind of very high-powered workstation, write a bit of Python, run the Python. That script might take 24 hours, right? So they spend a bit of time figuring out what that script should look like. They run it. It starts chugging through the data. It eventually runs out of memory. It crashes. They've already gone home, right, because it's like been 4 hours. They come back in the next day. They found the script that's crashed. And so they start it up again. They fix the bug, and they go again, and they iterate a few times. You know, now might be a week later. They've got their script working perfectly. But they potentially have lost their train of thought. They're trying to figure out a thing with this bit of Python, and they spent a lot of time doing computer science. And we hire them to be physicists and environmental scientists, so we can't expect them to work in this way, really. This is kind of akin to doing a batch job, right? They're working in this very batch paradigm, and it also involves a lot of copying data around, right? If they've all got individual workstations, they might have really high-powered Unix workstations under their desks, but it means they've got to copy loads of data out of the archive. We've got to put loads of spinning disks in these machines, and it slows everything way down. So I find this quite a common term within software development, especially. You know, I'm sure you've all heard the adage of developers are lazy, right? You write code so that you don't have to do a thing. But we use this to describe some of the ways that we handle the data internally. So I want to talk about a few different things that allow us to work lazily. And what I mean by lazily in this context is we want to leave the data where it is as long as we can. And we don't want to do any calculations until the very last minute. We want to know exactly what we're going to do with it. But we almost want to appear as if we're doing lots, but do it as little as possible. So I'm going to just tell you about a few libraries that really, really help us with this. Oh, it's not gone to next again. There we go. So Jupyter, if you haven't seen Jupyter, Jupyter's awesome. Right? We use this as a really, really good kind of first stab at giving our scientists particularly, but also our engineers, a good environment to start working from. So Jupyter Notebooks are a web-based application. You have usually a Python kernel running somewhere, but it's pretty language agnostic these days. You can run pretty much any kind of interpreter kernel somewhere. And you have this kind of, it looks a bit like a Google Doc, right? It's a web page. You have this kind of concept of cells. So you can have code cells where you write Python. And if you hold Shift and press Enter, it executes the Python on the remote kernel, and it brings you back whatever the response from that would be. So if you printed something, it would print underneath the cell. If you used matplotlib or some kind of library to plot an image, it puts that image underneath the cell. You can change the cell type if you want, so you can switch it to Markdown if I want to make some notes, if I want to write about what I'm doing. I don't have to do that in code comments. I can write that in Markdown. You get some kind of inline documentation. And it's got lots of nice fancy widgets and things like that. So you can, if you don't know what you're kind of wanting to explore, you could just not specify how to plot something, and it'll give you a slider, which is great. So in our situation of ensemble members, right? If we've got like 30 different cubes, and we want to kind of have a look at all of them, we could just say plot a cube, but not tell it which one, and it just gives us a slider. It gives us a plot and a slider, and you can slide it along, and it swaps between all those 30 models. And that's fantastic for our kind of workflow. The other neat thing about it is when you save the notebook, all of the output of the code, all of the images you've generated go into the file. And then if you commit the file and push it to GitHub, GitHub give you a nice preview version of that as well. So it's quite nice for us sharing things with each other within our workflow. So one of the libraries I wanted to talk about is Iris. This is something that we maintain internally. This is an open source library, so you can find it on GitHub at SciTools Iris. SciTools is like one of our internal organizations. And this as I said before, we store our data in weird file formats using kind of Z-order curves and different things like that to get really good compression on our data and make it quite portable for us. And this library helps you manage that, right? You can imagine not that many people use this file format. It's quite a specific, bespoke, scientific file format. So this library takes a lot of the pain out of that. But this library is also really clever in that it's lazy. So if I say, load a terabyte of data, it goes, done, I've loaded a terabyte of data. And it's like, well, I don't believe you. And it's like, well, actually, I've looked at the headers of all the files, and I've loaded all the metadata in, so I know what I've got access to, but I haven't actually touched any of the data on disk. And one of the great things about that is because what I might do straight away is say, right, I want to load all of Europe, so I'm going to load all of Europe. And I'm going to say, actually, I only care about London, so I'm just going to cut out the little bit of London in the next line of Python. And that's the bit that I'm going to work on. So because it hasn't loaded any data in, it's not going to discard loads of data that is pulled into memory. It's just going to now go, OK, I only care about these bits of these files. And I can do some operations on that. I can do some averages and means and different things like that that the sciencey people do. And because I've picked out my bit of London, when it runs the calculation on those, it only loads the chunks in from the files that cover London. So it allows it to be lazy in the fact that it's not loading loads of data and then discarding loads of data. So this is kind of what it looks like. Once you've loaded a cube in, you can print the cube, and you can kind of see we've got all the different layers. We've got different, let me have a look at this so I can see what it is. We've got different realizations. We've got the longitude and latitude. We've got some scalar coordinates in there as well. So this is kind of saying, I'm aware of this data. I haven't loaded this data, but this is what I'm aware of. This is what is in this cube that you can access. And that's great. It allows you to be quite iterative with your Python when you're developing something like that. But that's great, but when I run that on my desktop, if I want to do a calculation on all that data, once I've loaded it into Iris and I do a calculation, it will pull all those different bits of data into my machine and run it in a single thread within Python, right? Which is not ideal in terms of compute. You know, I might have a really powerful workstation, I might be running this on a mainframe, I might be doing it on something big and bulky, but I'm still stuck in this kind of serial world where, although I'm lazy about what data I load, I do have to load it all sequentially. So another library that we're really into at the moment is called Dask. If any of you have heard of Spark or tools like that, it's kind of a similar idea. This one's written in Python, which we have some interesting pragmatic issues around the fact that we have lots of science staff who they write Python as a byproduct of their job, right? They're here to do physics, they're here to do environmental science. They write Python in order to do that, but they don't care that much about Python. They're not, they're not software developers. They're not really interested in that kind of thing. And so they need to know the advantages of doing a thing before they're actually going to do it. They won't do something because it sounds cool. They'll do something because it's useful to them. So if we give them Spark and they do something wrong and it gives them a Java stack trace, they'll go, Java, I'm a Python person. I'm not even really a real Python person. I'm a kind of Python person. And I definitely don't want to look at a Java stack trace. So it's quite a big deterrent to them using that. So one of the factors that went into us picking Dask is that if it goes wrong, it gives them a Python stack trace at the very least. So at least they're slightly more within their comfort zone. But what Dask allows you to do is map out your compute. You install Dask on loads of machines, you have a big cluster, and it allows you to do kind of standard MapReduce jobs, it allows you to do quite small micro-batch interactive jobs. So if I'm going to load in a cube of London, say, and I want the mean over London, I can distribute all of that data into all of those machines. It can load each machine can load a little chunk of that into memory. It can do some means locally, and then one of the machines can do an aggregation, MapReduce, that kind of standard thing. And it's great. That's really cool for doing that kind of thing. But not a lot of our workloads work very well in a MapReduce paradigm because there's lots of cross-communication between different things. Different cells need to talk to each other. Different things need to communicate. So that's why we use supercomputers to run a lot of things. So you've got that really good bandwidth within the machines and low latency. But we might have graphs that look more like this, right? So you've got some steps that can be parallelized quite well, and then it needs to come together again, and then it might split out again, and then come back together. But Dask allows us to run this across a big cluster of machines and optimize where we can. And it does some very clever optimizations in terms of being lazy again. So if I queue up this graph, if you look at each of the circles, right, that is a discrete operation. That might be a line of Python or something. And so it's queued up this graph, but when I'm at the point of seeing this, it hasn't actually run anything. I've got my end value at the top. And it won't actually do anything with that end value until I try and print it, or until I try and actually look at it, until I try and realize what that value is. And then all of a sudden, all the compute sprays off, and it runs through this whole graph, and it does all the calculation. And one of the reasons it does that is because if I'm at this number at the top, I might then say, actually, I don't care about London, I only care about Shoreditch, right? And I'm going to cut down into a much smaller area. And then the compute graph can optimize by going, well, actually, that means I don't need this bit of the graph, and I don't need this bit of the graph. I only need to run up through these different columns, and I can parallelize these better. And it's much more intelligent about how it can run those things. So it doesn't realize until the very, very end, because it's trying to reduce the amount of calculation. And if I'm just trying to plot like a PNG to send to somebody, and it's small, and it knows that it only needs low-resolution data, it can do some averaging and downscaling and that kind of stuff. That's kind of the future where we're going with this. So this is a bit of a gnarly diagram. This is something that we've thrown together recently. This is a project we've been working on. It's called Jade. It's a collection of this stuff, right? This is how we've deployed this stuff for ourselves. As I said, we deploy lots of stuff on AWS. So recently, we took a load of data, put it into S3, which is really cool. We are looking at making that data open as well. So if you are interested, come and give me a shout. But you can see on this diagram that we've got a couple of auto-scaling groups, right? They're the interesting bits, right? One here and one here. And the top auto-scaling group gives each developer, each scientist, their own notebook environment, right? So you log in through the OAuth at the top, it spins up a box, or it starts a container somewhere, it'll pack you into some place within that stack, and you get your own notebook environment. You can install whatever dependencies you want, it's quite flexible. And then when you want to do some calculations on the data, you can connect to a scheduler. That scheduler may be whatever size. We might manually set what that size of that cluster is, or the developer or scientist might be able to set what size that is, and then they can run their calculations across the data. And that's great, but it introduces some really new and interesting business problems around the fact that if I have a 1,000 CPU hour calculation, I can run that on one machine for 1,000 hours, or I can run it on 1,000 machines for 1 hour. Right? Because I've got this scalable infrastructure, I can make these trade-offs, I can make these decisions. And that's awesome. That means I can get my work done 1,000 times faster, but it also means that I can spend 1,000 times more money for the organization. Right? If I'm massively scaling these clusters all the time, it builds up a big bill. So that's quite an interesting area for us, is looking at how we can kind of keep on top of that and maybe give people different budgets and things. So kind of, just to close up what I've been talking about, I hope this has been interesting for you. I just kind of wanted to share that we generate lots of data, and we try and make it as available as possible. You'll find lots of stuff on the UK government data website, so please have a look there if you're interested. There's a service on our website called DataPoint. We keep adding stuff to that, so please have a look. And we use and contribute to as many open source tools as possible, because it's only by collaborating with other people that we can really do this kind of thing. So, thank you very much.